Okay, hello everyone. We are going to talk about vectors today, and we're going to introduce you to the basics of what vectors are all about. So, to start off, define a vector. Well, there's lots of different quantities that exist in nature that can be described by single numbers. But vectors need two dimensions to describe them. They need both what we call a direction and a magnitude. And so, things that have a direction and magnitude, some examples are acceleration, forces, velocity, as opposed to speed. Velocity has a direction. And we often represent vectors by arrows. And these arrows have a head and a tail. And so it goes in this direction. And the arrow indicates the direction. The length of the vector indicates the magnitude. Okay, so let's move along here. And so we can take vectors, and we can add and subtract vectors. And so if I take u and v, I'll take u and v. So here's v. We'll make v black, and we'll make u blue. If I want to find negative, well, what I can do with vectors, I can take vectors, and then this is still vector v, because it has the same length and magnitude. This is still vector u, same length and magnitude. If I want negative v, all that means is I take my vector, and I go the same length, let me do a black one, same length, but in the opposite direction. This here is what we would describe as negative v. And if I could bold it by typing, I would do that. If not, I have to put a little arrow above the v to indicate that it's a vector. So this is negative v, this is positive v. If I want to add the vectors together, well, because I can move vectors around, here is negative v, and here's 1u, but I can take it, copy and paste it, and I can add the second vector here. And so if I then go, and if I add them and go in this direction, start at the head, follow the trail, this is the start of the tail, follow towards the head in this direction, this here is going to be this addition of these two vectors. I start from tail and I go to the head. And this would be the length and direction of minus v plus 2u. If I'm going to add these two together, let me undo a bunch of these scenarios here. If I was going to go and take v plus u, so here's v, take v plus u, take this vector here, there's plus u, and so v plus u then, if I do it in red, is this vector. But I want negative of it, so I am going to go in this direction here, this direction. So whether I put the arrow here or arrow here, doesn't matter, but this is negative v plus u. The scalar multiples is just when I multiply the vector by a number. So if I want to have 2u's, which I had, that's what scalar multiple means. Scalars have only magnitude. So 2 is a magnitude. 12 is a magnitude. There is no direction in here. If I say 12 kilometers per hour, that is still only a magnitude. If I say 12 kilometers an hour east, now it's a vector that has this direction east, and that is velocity. So let's take a look at some of these examples. The diagram shows a parallelogram as shown. AB is little a, and AB goes in this direction, tail, head. AD is vector B. Vector B, and it goes in this direction, AD. M is the midpoint of CD, so that means these two lines are equal. And N is on BC such that CN equals BC. Express CM, this whole CM Bn and Mn terms of A and B. Okay, so doing this is really all about following paths, is how I see it. I start at C, and I want to go to M with vectors that I know. So I want to go here. Well, if I start here, I do know that this vector here, CB, CM, is equal to CB plus BA plus AD plus DM. I could go all the way around to get to here. But I could do something a lot easier than that. I know that AB and DC are the same because it is a parallelogram. And if I want CM, this value here, I know then it's negative in the A direction. That's CD. I want half of it, so it's negative half A. BN, so if I want to go B to N, well, BN, well, this is B. That's an equivalent vector, B as well, so it's going to be 2B. And then finally, MN, M to N, let me clean this up a little bit so we can see what's going on. If I want to go from M to M, I have to follow this path here. So M to N is equal to M to C plus C to N. Well, M to C is positive half A, because it's in the opposite direction. C to N is equal to BC, which is the same as AD, because it's a parallelogram, and so there is our MN. Okay, some more basic notation. We know the base or unit vector notation. Well, if I have some vector, I'll do in 2 dimensions. If I have some vector that's, let's say this is 4 and this is 7, here is my vector, and this is the point 4, 7. I have a little vector here called I, which is length 1, and a little vector here that is called J. In 3 dimensions, I also have K. And so this point here, this would be 4I plus 7J. If it was in 3 dimensions, I would then go along and add some value K. But it works, 2 and 3 dimensions work similarly. And this is base or unit vector notation where you use I's and J's. We also have another kind of notation called column vector notation or components, and we take these points and we write them x, y. And so this is vector 4, 7. This is also what we call a position vector for the point 4, 7. So 4, 7 this way is the vector, this is the point. And it's written, and this is the position vector of the point. So if we consider this question here, you should pause it, try it yourself. So MP, I want to go from M to P. I know MN goes this way, NP goes that way. So I want to add these vectors. Well, if I'm going to do that, it's MN plus NP. Well, MN is simply 3I minus 2J plus 6K plus I plus J minus 3K. And with vectors, the base vectors components, we treat it just like algebra. So I get 4 I's minus a J plus 3K. And this here is going to be MP. PM then is equal to just going in the opposite direction minus MP. And so it's going to be negative 4I plus j minus 3k. And now if I want to go p to q, if I'm going to do p to q now, well, going p to q, I know I'm going to go here. If I follow the trail, I go to here, to here, to here. Or I could also go straight from p to m and then m to q, as I've got p to m already. So putting this together, pq is equal to pm plus mq, which is negative 4I plus j minus 3k plus mq, which is negative 2j plus 5k. And I add my components up. I get negative 4I vector minus 1j, a j plus a negative 2j, and then a plus 2k, just like algebra, and that is PQ. And so the mathematics of vectors with adding and subtracting is very similar to algebra. Position vectors, we already talked about the idea that if I have a point here, which is, let's say, 8, 3, this is the point here, then my position vector is 8, 3 for that point. So knowing that, let's try this example here. Position vectors of A and B, well, position vector A, we usually call OA because O refers to the origin, is going to be 3 minus 1, 2. And OB will be 5, 0, 3. The displacement vector, well, if I want the vector AB, let's just think here for a second. If I have OA, let's say this is the point A, and this is O, and I have OB, where this is B, I'm looking for vector AB, the displacement vector. And so if I'm looking for AB, I can go from A to O plus O to B, which is the same thing as writing OB minus, switch this around, switch it around, OA. And this is the head minus the tail. And that's, generally speaking, we always take the head, subtract the tail. And so AB is going to be OB, 5, 0, 3, the head, subtract the tail, 3 minus 1, 2, which gives me 2, 1, and 1. This calculation here, we will do time and time again. Head minus tail. Okay, so now we have points A, B, C, and D have these specific position vectors. Point E is the midpoint on the line BC. Again, you should pause the video, try it yourself, and then compare your answers and watch it if you need to. Okay, so we first want to find the position vector E, which is the midpoint of the line BC. Well, these are the position vectors. So if I want to find vector BC, I'm going to go head minus tail. But I'm also looking for the midpoint. And I can see from my formula booklet that this is the midpoint formula. And so if I want to find the midpoint of BC, I simply can use this formula here. And so OE, the position vector of E, I'm going to take these two vectors here. I'm going to add the components and divide by 2. So that's going to give me 12 divided by 2 is 6. 8 divided by 2 is 4. And 3 minus 3 is 0, 0. That is the point E. This is the point E. And so the position vector OE, or E, will be 6, 4, 0. With that, I want to now show that ABED is a parallelogram. And when we make parallelograms, we have to consider the order that we do it in. Ooh. We have to consider the order that we do it in. So, let me take that, I'm going to move this over here. And so I'm going to make a parallelogram, A, B, E, D. And each of these vectors is from O. So here's OA, OB, OE, and D. And we're going to show its parallelogram. In order to show it's a parallelogram, if I can show that two of the sides are congruent vectors, then it's a parallelogram because it's parallel and it has the same magnitude, which proves parallelogram. So I want to find vector AB and vector DE. And if they are equal, which I don't know, then it's a parallelogram. So finding AB is I go head, which is 503 minus the tail. So it's 503 minus 3, negative 1, 1, which will give me 2, 1, 2. DE, again, is going to be head, which is E, 6, 4, 0, minus tail, 4, 3, 2. Subtract them, I get 6 minus 4 is 2, 1, and, negative 2. Oh, I see it, the problem here. I forgot this minus sign here. Minus makes it a positive. So now I can see that AB is indeed equal to DE. They are equal. Therefore, since they have the same direction and magnitude, we have a parallelogram. So parallel vectors, if A and B are parallel, we can write A equal to TB for some scalar t. So I know then if it was like 2, 1, 3 is A equal to some value, let's say 4, 2, and 6, T would be 1/2 because now they're equal, they are parallel. They're not the same magnitude, but parallel, if they are parallel, they are called scalar multiples of each other. Scalar multiples, that's a good phrase to know. And this is going to be true if they are parallel. Let's try another example here. Given vectors A, B, C, as such, let's make a rough sketch of this. Here is going to be A, and here is going to be B. If we want to do A, 2 A's, here is 2A. Negative B, if I want negative B, I want to do this one. I'm going to take that, put it here, and copy, paste. I have 2 of them. I can see what it's going to look like. Oh. Here and here. There's are my come back. Here are my vectors here. And so roughly speaking, if I do it in red now, this would be my resultant vector here. There's my resultant vector there. That's 2A minus 3B. If I want to actually calculate it now, well, 2a is 1, 2, 7, minus 3b, negative 3, 4, 2, is simply, I can go 2, 4, and 14, plus 9, negative 12, and negative 6. Do the computation, I get 11, negative 8, and negative 8 is 2a minus 3b. The next question says, find the values of p and q such that c and a are parallel. All right, so if I'm going to do that, let me clear what I have so far. Let me clear this. What I have so far, I'll clear it off. So if I'm going to do the next step, p and q, they are parallel. So if they are parallel, that means a is equal to t, c. And so what I can say is this is 1, 2, 7 is equal to t, negative 2, p, and q. Well, from my x component, 1 is equal to negative 2t, so t is equal to negative a half. So then I can say, if this is true, that 2 is equal to negative a half p, and so p is equal to negative 4. I also know that 7 is equal to negative a half q, and so q is equal to negative 14, using the idea of parallel. And then finally it says, find a value of scalar k such that this is parallel to this vector. Well, let's do that. Okay, so now in D part, we want to find a value of scalar k so that a plus kb is parallel to this vector. So that means when I take vector a, 1, 2, 7, plus k of negative 3, 4, and 2, this has to equal some parallel vector, some scalar multiple of this. So in order to solve our scenario here, I'm going to make some equation. I'm going to look at my x component, 1 plus negative 3k is equal to 0. And I'll get rid of that so I can read it easier. I'll move the 1 over. And 2 plus 4k plus 4k is equal to 10t. But I also know that 7 plus 2k is equal to 23t. Now, I have 3 equations. This is my x, my y, and my z. 3 equations, 2 unknowns. I only need to take 2 of them, and I should check it in the third one. If I take this first one, I can see that 1 is equal to 3k, and so k is equal to 1/3. Here's what k is. I can take that and solve it for k here. 2 plus 4 times 1/3 is equal to 10t. And I get 6/3 plus 4/3 equals 10t. 10 over 3 is equal to 10t. And I know then that t is equal to 1/3. I should check the arithmetic here. The 7 plus 2 times 1/3 should be the same as 23 times 1/3. If I've done my math correct, this is going to be 21/3 plus 2/3 is indeed 23/3. And so I had to make 2 equations, 2 unknowns, and find k and t to confirm that they are indeed parallel. I'm going to stop here, and there's one more video here. No, I'm not. I'm going to keep on going, power through. Finally, the last idea here, we're going to talk about magnitude or modulus of a vector. Magnitude or modulus refers to what is the length of the vector. It's the length. So when we show our vectors by an arrow, It's basically saying how long is the arrow, the length of the arrow. And this is the calculation for our magnitude of a vector. It's from your formula booklet. So if I have points A and B with these position vectors, find the exact distance AB using vector methods. Well, AB I know is the head minus the tail. So it's 5, 2, 3 minus 2, negative 1, 5, which is 3, 3, and negative 2. Finding the magnitude, if I steal this formula here, if I use my formula, I know that it's simply square root of 3 squared plus 3 squared plus negative 2 squared, which then gives me 9 and 9 and 4, which is 18, which is 22 square root. That is the length or the exact distance of AB using vector methods. And the unit vector I referred to earlier is a vector of magnitude 1. And these are really handy when I have problems like an airplane, saying my airplane's flying 100 kilometers per hour, which is a speed, in the direction of 1, 2. Well, this direction, or this vector, is definitely not have a length of 100 kilometers per hour. And so we shrink it down for a magnitude of 1 in order to find the unit vector, or the vector that has this length. So if I want to find the unit vector in this direction, I have to first find the magnitude of A, which is going to be from my formula 2 squared plus 2 squared plus 1 squared. So I get 4 plus 4 plus 1. 9 is 3. And so if I take A, and if I divide it by 3, this now has a length. It is a unit vector. And I take 1 over the magnitude of A times A. That is my definition of a unit vector. Now that I know this is the unit vector, I want it to be 5 long. I take this unit vector and I multiply it by 5. And so now if I have 5/3, 2 minus 2, 1, this is a vector of length 5 in the direction of this. And that's the end of our vector basics.